All right, welcome back. So for this special Mastery Explainer, we're really bringing a journey to a close. We kick things off with the absolute basics, right? The foundational principles of how software is even put together. And now we're going to take it all the way to the bleeding edge. And the one thing, the thread that ties it all together, is this idea of wiring. So let's get plugged in and start the climb. Okay, here's the plan for our ascent. First up, we'll talk about the wiring revolution. What's fundamentally changed in software? Then, we'll dive deep into mastering internal connections before we zoom out to wiring the entire open web. After that, things get really interesting. We'll meet the new AI developer on the team, talk about a super important concept called the 10x rule imperative, and finally, we'll wrap it all up with a summary of what it means to be a sustainable architect. All right, let's get right to the heart of it. For decades, the job of a programmer was pretty clear. Write clever little bits of logic. Make a function do a cool thing. Well, that era is over. Gone. The main challenge today, the thing that keeps us up at night, isn't the logic inside one little box. It's the orchestration. It's the wiring that connects hundreds, sometimes thousands of those boxes into something that actually works. And honestly, the implication of this is it's huge. This one idea completely changes the definition of success for an engineer today. I mean, think about it. We're constantly pulling in third-party libraries, using services built by teams we've never even met. So who cares how brilliant your one little function is if it can't talk to anything else? Success isn't about that one brilliant function anymore. It's about the resilience of the connections between all the parts. Our job isn't being an artisan crafting a perfect wooden chair. It's being a city planner, making sure the roads, the plumbing, and the power grid all work together. We're orchestrators now. So to really get this, we gotta start small. We need to zoom way in and look at how we wire things together inside a single application. And when we're working at this level, there's a clear number one villain we have to defeat. It's a nasty, sneaky problem called tight coupling. Okay, and this slide just perfectly lays out the problem. So look at the left side. Imagine that code is inside a car object. The car is making its own driver, new driver. Simple, right? Wrong. We call this a hard-coded disaster because it's a trap. It looks easy, but it's incredibly fragile. Because what happens tomorrow when the driver class changes? What if now a driver needs a license to be created? Bam! Your car class is broken. And not just the car class. Every single piece of code in your entire system that created its own driver is now broken. It is an absolute nightmare to maintain. Now look at the right. That's the solution. Dependency injection. The car doesn't create the driver anymore. It just says, hey, I need a driver to work. Someone else has to provide it. And the big idea, the philosophy behind this whole shift is something called Inversion of Control, or IOC. And it's perfectly summed up by this classic line from Hollywood auditions: "Don't call us, we'll call you." See, in the old, broken way, our car object is making the call. It's actively reaching out to create a driver. With IOC, we flip that completely. We invert the control. The car just sits there and waits, and some other higher power, like a framework, calls the car and hands it the driver it needs. By giving up control, the object becomes way more flexible, and the whole system becomes resilient to change. It's a beautiful thing.
Now, if that sounds a little abstract, let's make it concrete with a couple of analogies. First, think of a restaurant. You don't walk into the kitchen and start cooking your own meal, right? Of course not. You sit down, and the waiter, that's our container, brings you a fully prepared dish. Or think about a construction site. The bricklayer doesn't show up and start mixing their own mortar from scratch. No, the foreman, the container, makes sure all the bricks and mortar are right there ready to go. So the bricklayer can just focus on one thing, laying bricks. That's exactly what inversion of control does for our code. It lets our components focus on their one job.
Okay, so you've decided to use dependency injection. Great. But hold on, it's not quite that simple. You've got choices, and trust me, making the right choice here is absolutely critical for a stable system. So let's break it down. Look at the table. Constructor-based injection is hands down the architect's choice, no question. Why? Two huge reasons. First, immutability. You make the dependencies final, so once the object is created, they can't be changed. That's a massive safety win. Second, testability. You can test your objects in isolation, no fancy framework needed. Now, setter-based, it has its place maybe for optional things. But field-based injection? Stay away. I know it looks easy, but architects hate it. It basically forces your nice, clean object to know about the messy details of the injection framework, which completely defeats the purpose of loose coupling in the first place.
All right, so we've got our house in order. We've mastered how to wire things up inside one application. So now, Let's zoom out. Way out. How do we wire completely separate systems together across the entire open web? And that question brings us to one of the biggest debates in software architecture: monoliths versus microservices. And this really is a massive strategic trade-off. On one hand, you've got the monolith. Everything is in one big, cozy code base. And you know what? It's super fast to get started. But that speed comes at a price. Eventually, it becomes what we call a one-language prison. You're stuck. And if one tiny part of your app gets a ton of traffic, you have to scale the entire thing. It's so inflexible. On the other hand, you have microservices, the ultimate form of loose coupling. You shatter your application into tiny, independent services. The freedom is intoxicating. You can scale just the parts you need. You can even write different services in different languages, what we call a polyglot approach. But all that freedom comes with a new, very difficult challenge. You now have to figure out how to wire all those little pieces together across the wild, unpredictable internet.
So, how do these microservices talk to each other? Well, the common language is the REST API. But the secret language, the one that makes them truly reliable, is understanding a property called idempotency. It's a weird word, but it's so important. Look, a GET request is easy. It's safe. It doesn't change anything. But the magic is with put and delete. They are what we call idempotent. And this is your system's critical safety valve. Why? Let me give you an example. Imagine a user hits the purchase button on your site and their internet connection glitches for a second. The request fails. What do? They click it again. If that purchase was a post request, which is not idempotent, you might have just charged them twice. But if it was an idempotent put to update their order status, they can click that button a dozen times. The outcome is always the same. They get charged once. That one concept is the difference between a rock-solid system and an absolute customer service nightmare.
Okay, deep breath. Because now we arrive at the frontier. We figured out how to get our own systems to talk to each other, but now we're wiring in a brand new developer, the most powerful and by far the most unpredictable team member we've ever had: artificial intelligence. And our attitude here has to be one of, let's call it vigilant optimism. We have to embrace the unbelievable promise of large language models, LLMs, while being acutely aware of the very real peril.
And this quote from Andrej Karpathy just nails the paradigm shift we're living through. The hottest programming language is English. Think about that. We're now communicating with these incredibly powerful models using the same REST APIs we just talked about, but the payload isn't structured data. It's plain English. But, and this is a huge but, we can never forget that LLMs are stochastic. They are probabilistic. They are guessing machines. They don't know anything. They're just predicting the next most likely word in a sentence based on all the data they've been trained on. That makes them amazing for generating ideas and boilerplate code, but it also makes them fundamentally unreliable when you need a single, correct, deterministic answer.
And this right here, this is the pivot point. This is the core warning of this entire explainer. Because all that speed that AI gives us, it's worthless. In fact, it's worse than worthless. It's actively dangerous if it comes at the expense of quality. We have to grapple with the very real danger of just writing bad code, but now at 10 times the speed.
So let me introduce you to a concept that should be burned into every developer's brain: Robert Martin's 10x rule. It's simple. The ratio of time we spend reading code versus writing it is at least 10 to 1. Just think about your own day-to-day work. Seriously, how much of your day is spent typing out brand new, fresh code versus staring at the screen trying to figure out what some existing code does? We read code to debug. We read it to add new features. We read it to track down that one impossible bug. The writing part is easy. The reading, that's where all the time, all the money, and all the effort goes.
And that is why AI is such a double-edged sword. Take a look at this data from GitHub Copilot. Now, to their credit, it's getting better. But even the new version is still suggesting insecure, vulnerable code more than a quarter of the time. So think about this through the lens of the 10x rule. If a developer just blindly hits tab and accepts that code, they didn't just save themselves an hour of typing. No. What they actually did was inject a 10-hour or 100-hour ticking time bomb of technical debt that is guaranteed to explode in the face of some other developer down the road, or even worse, in the face of a customer.
This is the bottom line. Human oversight isn't just a nice-to-have. It's not optional. It is a fundamental, non-negotiable requirement if you want to build systems that last. Using AI to just churn out unreadable, insecure, tightly coupled code isn't progress. It's the opposite of progress. You're just building a mountain of technical debt faster than ever before. The speed you write code means absolutely nothing if what you're creating is impossible to maintain. And that is the architect's job, to be the gatekeeper, to enforce the standards, and to protect the future of the system.
So let's bring it all home. We've been on quite a journey, right? From the tiniest wires inside an application to the massive cables connecting services across the web, and finally to this new AI frontier. But all of these ideas, they're not separate. They all weave together into one single unified philosophy, the mindset of the sustainable architect.
This table, right here, this is the blueprint. This is the culmination of everything we've talked about. So let's walk through it one more time and see how it all connects. It all starts at the foundation with internal wiring. We use the Hollywood principle, don't call us, we'll call you, to create decoupled components that are flexible and easy to test. Building on that foundation, our injection choice becomes paramount. We pick constructor-based injection because it enforces immutability and guarantees our objects are always created in a valid, trustworthy state. Once our foundation is solid, we can scale up to external wiring. We use REST as the common language for our microservices, giving us the freedom to innovate and scale. But in that chaotic, distributed world, we need API reliability. That's where Idempotency comes in as our life-saving safety valve, protecting us from data corruption. And finally, standing on top of all of this solid engineering, we can form an AI partnership. But we do it wisely, governing it with the unbreakable 10x rule. We always prioritize readability and security over the cheap thrill of raw speed. You see? Each principle is a stone in the foundation, building on the one before it, creating something truly sustainable. So I'll leave you with one final question, and I want you to really think about this when you go back to your own work. Look at the systems you're building. Are they just a house of cards, a collection of clever little bits of logic that are just waiting for a slight breeze to come along and knock the whole thing over? Or have you been paying attention to the connections? Are you building a fortress, secured by its wiring, built to withstand anything the world throws at it?